Hello and good afternoon friends, welcome to the CEC-UGC live lecture. Dear friends, as you know that we are carrying a series on chemical thermodynamics, and so far we have conducted numerous sessions on this very series. In our previous two lectures we discussed on expansion work. Today also we are going to carry the lecture forward, that is on expansion work, and specifically we are going to talk about isothermal and adiabatic expansion. And for this we have again with us in our studios Dr. Amit Kumar. Dr. Amit Kumar is Senior Assistant Professor in Department of Chemistry, Dayal Singh College, University of Delhi. So dear friends, let's welcome our guest Dr. Amit and let's try to understand more on expansion work. Hello sir, welcome to the EDISET lecture.
Hello and thank you so much.
So we are going to talk more on the expansion work, and we are going to talk on isothermal and adiabatic expansions. So sir, first of all tell us what kind of expansions are these, basically isothermal and adiabatic?
As we have already seen that previous lecture, we had a discussion of adiabatic as well as isothermal expansion work that was in relation to the expansion process with the working substances, the ideal gas. So today friends, we are going to have again a comparison and expansion session of the expansion work, but now this time we are going to see what are the thermodynamic changes which we do observe upon expansion of a real gas. That is, ideal gas is just a model of the gaseous system. So in reality what changes we observe when it comes to real gases and how expansion work, the quantification of expansion work is different from those of ideal gases, and also we would like to see at what side, at a lower side or a higher side, how the expansion work changes. So all these things will be the focus of attention in this lecture. So before we start with the discussion of expansion work in the van der Waals gases, or in terms of, or in other words the real gases, we first of all take up what we had a comparison of what we had done in the previous lecture, and we would like to start with that point where we did left. That is, we discussed isothermal as well as adiabatic work of expansion for expansion of an ideal gas as a working substance in the system. Moreover, we did quantified the various expressions for calculation of this work. Now we would like to see, if we compare between the work involved in adiabatic expansion and in isothermal expansion, which work is greater, the quantity of work which needs to be done for same change in volume, which is involved, that is the greater quantity is involved in which process, whether this is isothermal process or an adiabatic process. So for this, just let us have a look at this. First of all, let us once again consider an ideal gas that is present in a system with its initial state with pressure P1 and volume V1. If we carry out isothermal reversible expansion, then we reach to a final state where the volume is Vf, that is V final, and the pressure, instead of writing Pf, that is final pressure, we would like to write PISO, that is the final pressure in an isothermal expansion, isothermal reversible expansion of ideal gas. Now in contrast to this, let us have the same initial state of the system, and now let us carry out adiabatic reversible expansion. Then see, once again we will reach to the final volume that will be the same as that of the final volume in the isothermal process. However, we have written here PADI as the subscript, that is to show that PADI represent a variable which is just nothing but the final pressure value in an adiabatic reversible process with the same working substance. So starting with the same initial state, we will end up following two different paths. One is isothermal path and other one is an adiabatic path or a process, and we reach to a final state with a difference, that is the final pressure is in isothermal process is PiSO, and whereas in the case of adiabatic process it is PADI. So, now first thing which we would like to see, will there be a difference, because we have written the variable as a different subscript, that is PiSO and PADI. We would like to see, will there be a difference in their numeric value also. For this, let us have a consideration of first of all of isothermal expansion. For isothermal expansion of an ideal gas, initial state is P1 V1, which is related to the final state PiSO, and Vf, the final volume, by the relation P1 V1 equals to PiSO Vf. Now you see, here we are just having this equation of state under isothermal condition, that is PV equals to constant. Making use of that equation of state, we have just written P1 V1, that is the initial pressure volume, equals to PiSO into Vf, that is the final pressure and final volume. When we rearrange the equation, then what we get is Vf by V1 equals to P1 by PiSO. So, now with this is the ratio of final to initial volume. In the case of isothermal reversible expansion of an ideal gas, we get that is equal to initial and final pressure values as their ratio, since these are inversely proportional quantities. Now, coming over to adiabatic expansion, before we go about any kind of relationship between pressure volume, it is important to know that equation of state under adiabatic condition is PV raised to the power gamma as constant. So, here we would use, instead of P1 V1 equal to P final V final, we would like to write here is P1 V1 raised to the power gamma equals to PADI, that is the final pressure under adiabatic condition, times the volume, the final volume under adiabatic condition. Now again, now this time raised to the power gamma, instead of isothermal process where PiSO into Vf just was the final pressure volume, but here PADI into Vf raised to the power gamma. Now this we can also rearrange. What we would get is V final to V initial. Now we would get is the raised to the power gamma, that is equal to P1 by PADI. So it is very clear that initial volume which we have started with in both isothermal and adiabatic process, that is the same. Final volume where we did reach in the final state, that is also been the same. So it does mean now gamma makes a count. Gamma is the ratio of heat capacity under constant pressure to that of heat capacity under constant volume condition, and we all know heat capacity under constant pressure condition is higher. If that is higher, it does mean that gamma value will always be a positive value and having a magnitude greater than 1. So what it does mean? It do mean that Vf by V1 raised to the power gamma will always be greater than Vf by V1, because gamma is always having a value greater than 1 and has a positive sign. So it implies now Vf by V1 raised to the power gamma by having the adiabatic equation of state is equal to P1 by PADI. So instead of this left hand side, we have just written P1 by PADI. Now to the right hand side of this greater than sign, Vf by V1 is equal to P1 by PiSO, considering the equation of state under isothermal condition. So we have this relationship now, P1 by PADI is greater than P1 by PiSO. Now P1 cancels from both sides and we get 1 by PADI is greater than 1 by PiSO. Now when we rearrange it again, then what we get is PiSO is greater than PADI. It does mean if we carry out expansion of ideal gas from one initial state to final volume, that is from initial volume to final volume, under isothermal condition, the pressure, the final pressure of the system will be higher than that of the final pressure under adiabatic conditions. Now it is important to understand what implication this relationship which we have just derived has. This relationship has an important significance over here. Just have a look. Now with this we have PV isotherm diagram, and also it contains PV adiabatic diagram. If you could see this curve represent, which is here is represented by line, that is we have written isothermal. That means this PV curve, where this is the PISO, that is the final pressure, this curve represents the PV curve for the isothermal expansion process, whereas this curve with a final pressure, that is PADI, that represent the final pressure under adiabatic condition, and therefore this curve represent this curve represent the PV curve for the expansion process under the adiabatic conditions. So now it is very clear that area bounded by the below these curves represent the work involved in the various process, maybe the isothermal and the adiabatic. So we can see easily that area bounded by this curve, that is the isothermal curve, is greater than that of the area bounded by the adiabatic curve. So it is very clear that work involved under isothermal conditions for same change in volume, for same increase in volume from initial to final state is greater as compared to the work involved under adiabatic conditions. So final pressure, and moreover the final pressure under adiabatic condition is smaller as compared to final pressure under isothermal condition. So these are the generalizations, that is work involved under isothermal process for same change in state is greater when it comes to expansion work, and when it comes to adiabatic process, compared to the same volume increase as is done in isothermal condition, under adiabatic conditions work involved is less, that is less work needs to be done by the system to bring about same increase in volume as is being done in the isothermal process. Now this generalization, by virtue of similar manipulation of equations, we can have this generalization also, that is if we have these PV curves, if we keep instead of you see here the isothermal curve we also have adiabatic curve, that is if we want now that final pressure being kept constant, so we can see less volume change will be observed under adiabatic conditions as compared to a volume change which is being observed under isothermal conditions for same quantity of work being for same expenditure of energy. So therefore work involved under isothermal process is greater as compared to work involved under adiabatic process. That is what we want to make a generalization. Now having said this, so till this time we have completed the discussion of expansion work of all the ideal gases. Now we would like to understand what way the expansion work and its quantification and thermodynamic changes in various other thermodynamic parameters such as internal energy, enthalpy and other thermodynamic variables, how the changes will be different from those of the changes observed when the expansion work was studied for ideal gases. So now it is time to understand what happens in the situation of van der Waals gas, that is a real gas. Basically to model a gaseous system, we have introduced an ideal gases system, where we had two main important considerations, that is volume occupied by the gaseous chemical species is very less as compared to the volume in which the gases are present. So that is the volume which is of the constituent chemical species has been excluded there in the model. Moreover, we had also modeled the ideal gases as the gases in which there is no force of interaction which do operate between constituent chemical species. So these were the two main important considerations while modeling the gases as ideal gases. Now when it comes to real gas, in reality this is not true. The proof for the fact that there occurs interaction between constituent chemical species lies in the fact that when we bring about cooling, then upon cooling the system we observe condensation also, and finally we can get liquid state upon cooling the gases and also the solid state. So it is a clear indication that in the gaseous phase also there was some forces of attraction which was operating between the constituent chemical species. So Another point is that volume occupied by the gaseous species is very less as compared to the volume in which the volume which was accessible to the gaseous chemical species in the ideal gas model. So, we need to make correction for both these two considerations, and van der Waal was the one which made these corrections, and to the ideal gas equation he made corrections corresponding to the forces of interaction operating between the constituent chemical species, and also he introduced the portion of correction to the volume term, that is excluded volume. This is the first time he introduced and gave the equation of state, that is now known as van der Waal equation. So, using this van der Waal equation instead of ideal gas equation, we would like to develop the expression for work, internal energy, enthalpy change and so on under isothermal condition and under adiabatic condition. That is how the aim of today's lecture is to have an understanding of, have an appreciation of the quantities of the quantification of these changes in thermodynamic parameters when the expansion work is observed in the case of real gases, or in other words the van der Waals gases. So, let us have a look at that. Is first of all, let us have a consideration of isothermal expansion of a van der Waal gas. In this, again characteristic is just been the same as that of ideal gases. Here also, if this is isothermal expansion, so here also temperature remain constant. If temperature remain constant, therefore delta T is equal to 0, there is no finite change in temperature. Now, if we consider reversible expansion of van der Waal gas, then dW, that is the small quantity of work involved, infinitesimal quantity, that is equal to minus P(ext), the external pressure, into dV. Now, if we carry out expansion work under reversible conditions, then it is for sure that external pressure would only be different from that of internal pressure only by a very small amount, that is dP. In the case of expansion process, it will be slightly lesser, so negative sign will operate, and in the case of compression process, external pressure would be just little higher than that of external pressure, then the positive sign will operate, will come into account. And since this dP, there will be only a very infinitesimal change in infinitesimal difference between internal and external pressure. So, we would say that for all practical purpose this dP is very small, and for all practical purpose external pressure is almost same as that of internal pressure. And now, it is the van der Waal equation of state, van der Waal equation gases equation that we can make use of to have the quantification of pressure, the internal pressure, that is nRT by V minus Nb, where N is number of mole, R the gas constant, T the temperature, V the volume, and the number of moles again, and then B here represent the term corresponding to excluded volume. So, therefore, V minus Nb from this total volume of the gaseous system minus Nb, that is the volume corresponding to the volume being occupied by the constituent chemical species has been subtracted. So, now this then become the actual that much volume there, because that volume was excluded. Now, minus n square A by V square, and again the number of moles, V again the volume A. A is a measure of forces of attraction which do operate between constituent chemical species. So, pressure now will not just be related to nRT by V, but will be accounting for excluded volume, and also will be calculated using taking into account the forces of interaction. That is how van der Waals equation is very important for real gases. Now, having said this, it means P internal would be this much, would be given by equation 3. So, it means we can make use of equation 2 and equation 3 in equation 1, that is P(ext) would be just similar to that, would be just congruent to P internal, and therefore, instead of making use of P(ext), we can make use of P internal, P(int) in equation 1, and for P(int), P internal, we can make use of equation 3 and can substitute this whole expression in equation 1, and ultimately what we get is dW equal to minus P ext dV almost equal to minus P internal dV, and that is minus sign here. Instead of P internal, we just make use of van der Waals equation and we substitute for P internal the right hand side expression. Now, this multiplied with dV, the volume, small volume change, and now we, for calculation of finite quantity of work involved in the expansion process, we can integrate this whole equation, as integral of left hand side would be equal to the work involved, and that is equal to minus integral V1 to V2 nRT by V minus NB minus n square A by V square into dV. Now, we can have these in two parts, that is integral minus integral V1 to V2 nRT by V minus NB multiplied with dV, like this, and second part integral V1, here should be V1, sorry, and V1 to V2 n square A by V square dV. Now, which we can integrate n, the number of moles once the system is taken, its composition remains constant. So, n number of mole will be constant, will not change. R, the gas constant, that also remains constant. Isothermal process, so temperature constant, that can also be taken out of integral sign. Now, therefore, we have within integral V1 to V2, we have dV by V minus NB plus, we can take n number of mole constant, forces of interaction which do operate between constituent chemical species, that would also be a constant. So, we can take them out over here. So, therefore, n square A we can take it outside of integral, and V1 to V2 we can integrate dV by V square. What we get as an integration is minus nRT ln. Now, this integration of this quantity dV by V minus NB is ln V minus NB from V1 to V2 plus n square A minus sign. Now, because dV by V square, its integration is minus 1 by V. So, we just have written here minus 1 by V within limit V1 to V2. Now, we can substitute for the limits also, nRT ln V2 minus NB, then minus ln V1 minus NB, and then second term plus n square A. Now, again here in the bracket minus 1 by V was the integral within limit V1 to V2. So, minus 1 by V2 minus 1 by V1. So, now W equal to nRT ln, we can log, we know that log A minus log B equal to log A by B. So, we can make use of that logarithm formula, and that W equal to nRT ln V2 minus NB divided by V1 minus NB plus the second term n square A. Now, minus 1 by V2 minus plus 1 by V1. So, W now therefore equal to nRT ln V2 minus NB by V1 minus NB minus n square A, we can take it here 1 by V1 minus V2 it was. Now, if we take minus sign common from this second term, as instead of writing plus here we have written minus. So, it means minus we have taken common out of the bracket term, it become 1 by V2 minus 1 by V1. So, we have calculated the value of work involved, that is if we know the volume change, that is V1 and V2, if we know number of moles, if we know the excluded volume and the A parameter, that is which is a measure of interaction, forces of attraction which do operate between constituent chemical species. If we know all these values at a particular temperature, we can calculate the work involved in the expansion process. Now, having said this, it is time for us to look for expression of delta U, that is the change in internal energy. Now, for this, let us consider first of all thermodynamic equation of state. I am just using here thermodynamic equation of state, this equation, that is given by equation 6, that is applicable for all systems, maybe the gaseous system, maybe the liquid systems, maybe the solid systems, or under reversible conditions or irreversible conditions, under all conditions and for all state of systems, this equation is applicable, that we will derive it at some later stage. So, here I am just using it, that is equation 6 is called thermodynamic equation of state, according to which delta U by delta V at constant T temperature, that is we will read it as the change in internal energy with respect to change in volume under condition of constant temperature equal to T, the temperature times change in pressure with respect to change in temperature under constant volume minus pressure term. So, it is therefore, since P from van der Waal, we have just seen that from van der Waal equation P equal to nRT by V minus Nb minus n square A by V square. So, we can make use of this equation, that is P, in equation 6. We would just see, we would like to because in equation 6, if we see that we have T delta P by delta T at constant V term. This term which we can get from by differentiating the van der Waal equation, that is, if we differentiate van der Waal equation, that is nRT by V minus Nb minus n square A by V square, that is bracket term is van der Waal equation, that is equal to P. So, therefore, it means if we differentiate equation number 7 with respect to temperature, we would be able to get delta P by delta T at constant V, and whatever expression we will get, we can substitute back in this equation, equation number 6, and we can get the value of delta U by delta V at constant T. Let us have a look at how we can do this, we can achieve this. That is, if we differentiate delta P by delta T at constant V, that is equal to del by del T. Instead of P, we have made use of the expression in the van der Waal equation, that is nRT by V minus Nb minus n square A by V square here in this equation. And therefore, now if we differentiate it with respect to temperature, we see that in the first term in the bracket there is temperature, but in the second term there is no term which depends on, which is a measure of temperature, therefore directly, because volume, we are keeping volume constant. So, under constant volume condition, second term has only number of moles, A again a constant, V which is being kept constant. So, therefore, second term is just a constant, will not vary with temperature under constant volume condition. So, it means this differential of second term would be 0, and the differential of first term is n R by V minus Nb, because dt by dt that is equal to 1. So, we have got delta P by delta T at constant V value, that is equal to n R by V minus Nb. So, which we can now make use of the equation which we just derived, that is delta P by delta T at constant V. Instead of this in equation 6, like here we have written, we can substitute the value nRT by V minus Nb for delta P by delta T at constant V in this equation 6. So, we get nR by V minus Nb multiplied with T temperature. Over here we have written T here. Left hand side is just been the same, minus sign is here as compared to equation 6. Now, instead of pressure here, we can make use of van der Waal equation, that we can write in the bracket term here. You please see on the projection itself, that is van der Waal equation we have written in the bracket term as instead of P, the internal pressure, making use of van der Waal equation. So, we finally get this equation, and now we can rearrange this also. Before rearranging, just have a look. We have just written nRT by V minus Nb from in this equation as is just same as in this equation. Now, we can open up the terms in the bracket, and we can write minus nRT by V minus Nb here. So, minus sign is here in this equation. So, minus minus gets multiplied and become plus n square A by V square. Now, it is easily seen that nRT by V minus Nb minus nRT by V minus Nb. So, these two terms do cancel. So, what we get is delta U by delta V at constant T equal to n square A by V square, that is given by equation number 9. Now, it is well known that internal energy is a function of temperature and volume. So, if it is a function of temperature and volume, we have already discussed it a number of times when we discussed the first law of thermodynamics. So, therefore, if we want to determine the change in internal energy, that is, we can write du equal to delta U by delta T at constant V dt plus delta U by delta V at constant T dV. Now, since under isothermal process we are considering this expansion dt is equal to 0. So, first term in this du in the right hand side of du expression is equal to 0, and the second term involves one partial differential coefficient delta U by delta V at constant T, which from equation 9 we have its value, that is n square a by v square. Therefore, in equation 10 we can put instead of delta u by delta v at constant t, n square a by v square value, and this first term is 0, and that is how we get du equal to delta u by delta v at constant t dv. Now, having said this, instead of delta u by delta v at constant t, we can write n square a by v square dv. We have just derived that this equal to this. So, now which we can, for a finite change, we can integrate this the equation 11 and we can get delta u, that is delta u equal to v1 to v2 n square a by v square dv equal to, now n is constant, a is constant, and only volume is changing. So, therefore, dv by v square, that has already we have discussed what would be its integral value, that is minus 1 by v. So, it become minus n square a 1 by v2 minus 1 by v1. So, this is equation number 12 which we get, that is till now we have obtained the quantity of work involved, we have obtained its expression. We have also derived the value of delta u, the internal energy change under reversible condition, same is the quantity of work involved, and now therefore, it is time to find out the expression for Q, that is the heat involved in the expansion process. From the first law of thermodynamics, we know that Q, the heat involved, equal to delta U minus W. Now, instead of delta U, we can substitute this expression, we have just derived minus n square A into 1 by V2 minus 1 by V1. So, minus del Q equal to minus n square A bracket term 1 by V2 minus V1, this represent delta U, the change in internal energy. Now, W is minus nRT ln V2 by V2 minus NB, V1 minus NB plus n square A 1 by V2 minus 1 by V1. Since this was minus, so minus minus become plus, so we have just written plus here, we have written just plus here. So, Q becomes this, just by substituting the expression of delta U and W, which we have just derived in this first law equation, we get Q equal to this equation. Now, here you can easily see this n square A 1 by V2 minus V1 has a negative sign, and this n square A 1 by V2 minus V1 has positive sign. So, both these two terms cancel, and what we get is therefore, Q equal to n R T ln V2 minus NB divided by V1 minus NB. So, what we have done as a summarization till the time, for reversible expansion of a van der Waals gas, we have derived expression for Q, W and delta U. Now, it is time for developing an expression for delta H also. Since delta H equal to delta U plus delta PV, therefore, we have written delta U H equal to minus. Now, instead of delta U, we can substitute the value of delta U expression, which we have just derived, that is minus n square A into 1 by V2 minus 1 by V1 plus delta. Now, within this bracket there is van der Waals equation that represent the pressure and multiplied with volume. Now, this we can expand minus n square A 1 by V2 minus 1 by V1 plus delta nRT V divided by V minus NB minus n square A by V. So, therefore, minus n square A 1 by V2 minus V1 plus delta nRT V divided by V minus NB minus delta n square A. So, this is just merely a the two terms have been taken as separately, and then minus n square A 1 by V2 minus 1 by V1 plus nRT. Now, this n is constant, R is constant, temperature constant under isothermal condition. So, we only have a difference of volume. So, therefore, delta V by V minus NB, same here minus delta n square A by V. So, n square A which we can take outside, and therefore, ultimately we get this expression as delta H equals to minus 2 n square A 1 by V2 minus 1 by V1 plus nRT V2 by V2 minus NB minus V1 by V1 minus NB. So, ultimately we get this equation. Now, to this, if in order to make it further simplified, we can add minus and plus NB values here, and therefore V2 minus Nb, and this equation finally transforms to V2 minus Nb by V2 minus Nb plus Nb by V2 minus Nb minus V1 minus Nb divided by V1 minus Nb minus Nb by V1 minus Nb. So, it becomes 1 plus Nb by V2 minus Nb minus 1 minus Nb by V1 minus Nb, 1 cancels. So, finally, we get, so this is how we derive the value of delta H also, that is equal to minus 2 n square A 1 by V2 minus 1 by V1 plus nRT into in bracket within bracket Nb by V2 minus Nb minus Nb by V1 minus Nb. So, it means therefore, we have derived the quantities of heat involved, the work involved, its negative value over here, and the change in internal energy. When we carry out expansion of van der Waals gas under reversible conditions. So, these are the values Q, that is nRT ln V2 minus B divided by V1 minus B, and you can see and compare its value by ideal gas, that is nRT ln V2 by V1. Similarly, the work involved is different from that of reversible expression of work involved under isothermal condition. For ideal gas is this, and for real gas has the terms corresponding to excluded volume and the A, that is the which is a measure of forces of attraction which operate between the molecules, and the internal energy is equal to minus n square A into 1 by V2 minus 1 by V1. So, you see it is very clear, by just making use of these equations we can easily see that minus W is, that is nRT ln V2 minus B divided by V1 minus B, that is this term, that is heat Q. So, the first term in minus W expression is heat Q, and second term is delta U with a negative sign. Now, since delta U is minus n square A bracket 1 by V2 minus 1 by V1, so if we multiply it with minus sign, so it becomes plus n square A into 1 by V2 minus 1 by V1. So, basically for isothermal expansion of a van der Waals gas, we have minus W equal to Q minus delta U. Now, this equation has important implication. What is the implication? It says that whatever the heat we give to the system, that has several portions. One portion of this heat given to the system is being given to the system in order to increase its internal energy. If we subtract that portion from the total quantity of heat which is being taken by the system, then that is equal to minus W, because work is done by the system has a negative value, and minus W therefore represent quantity of work being done by the system. So, here it is important to note that some portion of heat that is used to raise internal energy. Now, question arises, how the internal energy gets raised, because temperature is kept constant. For the ideal gases we all know internal energy remains constant. Why? Because as per the Joule's law we all know that energy, internal energy is a function only of temperature for all ideal gases, but for real gases the internal energy do changes even under isothermal condition. Therefore, it is a function of volume also. So, how what changes in how the internal energy changes? You see, whenever we have observed that whenever expansion occurs, then volume gets changed, volume is increased. When volume is increased, now there is greater volume which is accessible to the gaseous chemical species as compared to the earlier situation where less volume was accessible. So, now as greater volume is accessible, now the average distance which I talked about in my previous lecture also, the average distance within a greater volume when it is accessible, the average distance between the constituent chemical species do increases. In order to bring about this spacing, we need to supply the energy to the system, and that energy which we are supplying in terms of heat, and its portion is going to get it stored in terms of internal energy. That internal energy is by virtue of potential energy. That is, whenever there occurs forces of attraction at a certain distance, there will be different potential energy, and whenever the spacing between the molecules increases, their potential energy will get enhanced, and it is because of that potential energy factor, the internal energy of the system, we observe a change, that is a increase. So, whatever the heat system obtains, that is used to do work, and the rest is used to raise the internal energy of the system for the case of real gases, because under isothermal condition for ideal gases the internal energy remain constant. However, for real gases it do increases, and that increases because of an increase in potential energy by virtue of creating spacing between the molecules, that is by increasing the average distance between the constituent gaseous chemical species. So, now let us have draw our attention to this is what is we have discussed the reversible changes. Now, it is time to consider the irreversible expansion also. Here again dW equal to minus P ext dV and dW equal to minus P ext V2 minus V1. So, here we are just going to have only this much as the expression for work. Now, since internal energy is a state function, so it does not mean if you bring about same change in state, same change in volume, it does not mean whether, and same temperature, same volume, it does not mean whether you have followed a reversible path or an irreversible path, the total internal energy change will be the same. So, we are making use of same equation for internal energy even for the irreversible path. Now, what is the heat involved? That is equal to the change in internal energy and added to which is the amount of subtracted from which is the amount of work, that is minus P ext V2 minus V1, that become plus P ext V2 minus V1. So, here for the irreversible process the quantity of work involved will be lesser, but the expression will be given by W equal to minus P ext V2 minus V1. Now, let us talk about free expansion also. Free expansion means when there is no opposing pressure, P opposing external pressure is 0, and that situation W will be equal to 0. So, for free expansion there will be W equal to 0, but there will be again W will be equal to 0, but there will be a change in internal energy. That change in internal energy, as we have just described, when you carry out expansion, greater volume is accessible, there is greater average distance between the constituent chemical species. To do that, we need to increase the potential energy of the system. By virtue of this increase in potential energy, we observe a change in internal energy of the system, that is internal energy gets raised, and Q is equal to minus delta U, Q equal to delta U. So, therefore, Q is again the same expression, delta U is again the same value as is for the reversible expansion. Now, it is time to discuss the adiabatic expansion also. For adiabatic expansion, we have the characteristic, that is Q, the heat involved is 0. That is, there is no heat exchange is possible between the system and the surrounding. So, therefore, Q equal to 0, and when Q equal to 0, from the first law of thermodynamics, it is very clear that delta U is equal to W. Now, if we want to quantify delta U, let us consider again U is a function of temperature and volume, and differentiate it to determine infinitesimal change in U. And we have already seen that delta U by delta T at constant V is nothing but NCVM, that is heat capacity under constant volume condition, molar heat capacity. When you write, then you need to multiply with n number of moles. Therefore, du equal to NCVM dt plus delta U by delta V at constant T, and this term we have just derived even for isothermal condition. So, because delta U by delta V at constant T is under isothermal condition, which we have just derived in this lecture itself just previously, that is n square A by V square. So, we substitute over here and multiply it with dV. Now, for a finite change we need to integrate this equation. So, we integrate this equation, what we get is NCVM integral T1 to T2 dt plus n square A integral V1 to V2 dV by V square. So, delta U equal to NCVM, now its integral is T2 minus T1, T within limit T1 to T2. So, what we get T2 minus T1 minus, now this here n square a integral dV by V square, its integral is minus 1 by V. So, if we take minus common, so it become minus n square a 1 by V2 minus 1 by V1. So, delta U equal to n CVM T2 minus T1 minus n square a 1 by V2 minus 1 by V1. Now, let us have a discussion of the fact that we all know that under adiabatic condition, there is a change in whenever we observe expansion work, that is when the volume changes. There is no possibility of exchange of heat with the surrounding. Work is being done by the system. That would be that would be at the expenditure of internal energy of the system. So, what it does mean that internal energy will undergo a change. At the expenditure of internal energy, we are observing expansion work under adiabatic conditions. So, therefore, it does mean that whenever expansion occurs, that is the volume changes, so also changes the internal energy, and internal energy is a function of temperature. So, it means both temperature as well as volume undergoes a change. So, if suppose we have a availability of initial volume, the initial state, that initial temperature, initial volume and also initial pressure, then we have finally we get to know the value of final volume, then it becomes important to understand what will be the final temperature also. That is, we need to bring about calculation of temperature change also. So, for this let us have a discussion of how to calculate temperature change, that is the final temperature of the system. So, therefore, for a van der Waals gas, let us again consider equation, van der Waals equation, that is P equal to nRT by V minus Nb minus n square A by V square. Under adiabatic condition, du equal to dW. Why? Because Q is 0 and dW equal to minus P dV. So, left hand side we can put the expression for dW, that is n CVM dt plus n square A by V square dV. If you would have noticed, we had just derived here, and that is equal to minus P into dV, that is P is from the van der Waals equation and multiplying each term with dV. So, this equation we get. Now, what we need to do is, if we compare the left hand and right hand side of this equation, n square A by V square dV term is common. So, that gets cancelled and we get CVM dt equal to minus RT by V minus NB into dV, which we can rearrange separating variable CVM dt by T equal to minus R dV by V minus NB. Now, we can integrate this equation. What we get is, provided the fact that suppose the heat capacity under constant volume condition CVM is independent of temperature, within temperature range initial and final temperature. If so, then we can take it as constant and we can integrate this equation left hand side dt by T, whose integral become ln T, and ln T within limit T1 to T2 is ln T2 by T1. And therefore, this is the left hand side expression. Similarly, right hand side expression is minus R ln V2 minus NB by V1 minus NB, which we have just seen earlier also. So, therefore, CVM by R ln T2 by T1 equal to minus ln V2 by minus NB by V1 minus NB. Now, what we need to do is, this is A log B is just nothing but log B raised to the power A. Making use of that logarithmic equation, we can modify this equation as ln T2 by T1 CVM by R equal to ln V1 minus NB by V2 minus NB. And therefore, T2 by T1 taking anti-logarithm on both sides, what we get is T2 by T1, that is equal to just a minute. So, what we get is the temperature ratio raised to the power CVM by R equals to a expression which has volume, initial and final volume, and excluded volume term also. So, what we get is finally this T V minus N B. By manipulation of these equations, what we get is T V minus N B raised to the power R by C V M equals to constant. So, therefore, by just separating the variables, we get is the final temperature equal to T1 into V1 minus Nb by V2 minus Nb raised to the power R by CVM. So, we can get the final temperature also. Now, expression of enthalpy change can again be obtained by making use of delta U and the delta PV term in the delta H equals to delta U plus delta PV equation, and finally, we get in enthalpy change again here as n CVM T2 minus T1 minus 2 n square A 1 by V2 minus 1 by V1 minus n R V2 T2 by V1 minus Nb minus V1 by V1 T1 by V1 minus T1 V1 minus Nb. So, this is how we can develop equations for change in internal energy, work involved and the enthalpy change. Now, under irreversible conditions, W equal to minus P Ex T V2 minus V1, again since Q equal to 0 for adiabatic conditions, making use of the first law of thermodynamics, we can see when Q becomes 0, delta U equal to W. So, therefore, delta U equal to minus P Ex T V2 minus V1. So, again here we can look for the temperature change, that is temperature of the gas after expansion. As I said, it is very important to obtain the value of final temperature, that is very important, because both temperature and volume are changing, and if we through experimental observations we are being able to note only the volume change, or if only the volume change is being given and initial temperature is given, so final calculation of final temperature become important. So, here again using the making use of same equations, that is du equal to dw, and making use of delta u by delta v at constant t and delta u by delta t at constant v, such partial differentials we can write for dw also, and we can obtain a final value of temperature change. So, here T2 is little T2 dash, I have written here T2 dash, because in the irreversible conditions the quantity of work involved will be less than that of the reversible condition. So, therefore, the less change in temperature will be observed. So, this is what needs to be understood from these expressions. Similarly, delta H expression can also be obtained just by putting the value of delta U and delta PV terms as we had derived. So, therefore, now coming over to the last point, that is the free expansion in this lecture. For free expansion, we have already seen that the work involved is 0. Why work involved is 0? Because there is no opposing force, there is no P external is 0, and therefore, W equal to minus P external dV, that is P external is 0, it means W, the work involved is 0, and moreover the heat involved Q is also 0. And now here, since we are doing it free expansion, Q0, W0, the first law of thermodynamics says delta U0. However, we still observe a temperature change, that is temperature is again we find that temperature here also it decreases in the free expansion also. When it was decreasing in the case of reversible adiabatic expansion, that was understood. That was understood because as I said, the temperature decreases because the work is done at the expenditure of internal energy is a function of temperature, and because internal energy decreases, and therefore with the temperature also decreases with the decrease in internal energy. So, it is very clear for reversible expansion. For intermediate irreversible expansion also, in the case of adiabatic expansion, it is very clear that temperature change would be observed. But here the situation is little different. Difference in a way that since no work is being done, W is 0, internal energy change is 0. Why? Because heat exchange is also not possible. So, Q is 0, W is 0, yet and therefore, first law equation says delta U is also 0. It means there is no change in internal energy, no change in no work is being observed, no heat exchange is being made. So, yet we observe a change in temperature. What it does mean? Why there is a temperature change? Why there is a decrease in temperature when that expansion work was observed? The reason is that although there was no work which was done, but when expansion occurs, as I said earlier, it leads to increase in volume, and within a greater volume the average distance again comes into play. That increases between the different between the constituent chemical species, and that leads to modification of forces of attraction which operate between the constituent chemical species, and that results in increase in potential energy. And so therefore internal energy we do not observe a change. It means the kinetic energy of the constituent chemical species has just changed into potential energy. That is, kinetic energy is now manifesting itself in terms of potential energy. That's it. That is the reason temperature is a reflection of average kinetic energy of molecules. As a result, temperature decrease has been observed. However, internal energy we do not observe any change. Work is there is no work done, no heat exchange, no internal energy change, but temperature decreases. Thank you so much.
With this note, sir, thank you, sir. Thank you so very much for giving us a productive session once again. And dear friends, we would be meeting again and we would be discussing more on chemical thermodynamics very soon. Till then, take care, goodbye, and keep mailing us at info.cec@nic.in so that we would be able to get your feedback. We would be able to know how much you are learning and what else we could do for you. Thank you, sir. Thank you so very much.